Welcome back to our discussion on the lesson of gravitation. Today we will be resuming the topic from where we left in our previous class. In our previous class, I had told you that Sir Isaac Newton gave the universal law of gravitation, according to which every object in this universe attracts each other with a force that is directly proportional to the square of the product of the masses and inversely proportional to the square of the distance between them. Using that, we had obtained an expression for gravitational force as F equal to g m1 m2 by r square. Now a basic question arised that how could Newton derive the inverse square law? For that we need to understand Kepler's law, because it was from Kepler's law that Newton was able to derive the inverse square law. Now before that, I would like to show you the pictures of some eminent astronomers who had made significant contributions in the field of astronomy before Johannes Kepler gave the laws of planetary motion. Johannes Kepler was a German astronomer, mathematician, and astrologer. He is a key figure in the 17th century scientific revolution, best known for his laws of planetary motion and his books Astronomia Nova, Harmonices Mundi, and Epitome Astronomiae Copernici. These works also provided one of the foundations for Newton's theory of universal gravitation. Kepler lived in an era when there was no clear distinction between astronomy and astrology, but there was a strong division between astronomy branch, a branch of mathematics within the liberal arts, and physics, a branch of natural philosophy. Kepler also incorporated religious arguments and reasoning into his work, motivated by the religious conviction and belief that God had created the world according to an intelligible plan that is accessible through the natural light of reason. Kepler described his new astronomy as celestial physics, as an excursion into Aristotle's metaphysics and as a supplement to Aristotle's On the Heavens, transforming the ancient tradition of physical cosmology by treating astronomy as part of the universal mathematical physics. Kepler's first major astronomical work, Mysterium Cosmographicum, that is a cosmographic mystery that was published in 1596, was the first published defense of the Copernican system. Kepler claimed to have had an epiphany on 19 July 1595 while teaching in Graz, demonstrating the periodic conjunction of Saturn and Jupiter in the zodiac. He realized that regular polygons bound one inscribed and one circumscribed circle at definite ratios, which he reasoned might be the geometrical basis of the universe. As indicated in the title, Kepler thought he would reveal God's geometrical plan for the universe. Much of Kepler's enthusiasm for the Copernican system stemmed from his theological convictions about the connection between the physical and the spiritual. The universe itself was an image of God, with the sun corresponding to the Father, the stellar sphere to the Son, and the intervening space between to the Holy Spirit. His first manuscript of Mysterium contained an extensive chapter reconciling heliocentrism and biblical passages that seemed to support geocentrism. Though the details would be modified in light of his later work, Kepler never relinquished the Platonist polyhedral spherist cosmology of Mysterium Cosmographicum. His subsequent main astronomical works were in some cases only further developments of it, concerned with finding more precise inner and outer dimensions for the spheres by calculating the eccentricities of the planetary orbits within it. In 1621, Kepler published an expanded second edition of Mysterium, half as long again as the first, detailing in footnotes the corrections and improvements he had achieved in the 25 years since its publication. In terms of the impact of Mysterium, it can be seen as an important first step in modernizing the theory proposed by Nicolaus Copernicus in his De Revolutionibus Orbium Coelestum. Whilst Copernicus sought to advance a heliocentric system in his book, he resorted to Ptolemaic devices in order to explain the change in planetal's orbital speed, and also continued to use as a point of reference the center of the Earth's orbit rather than that of Sun as a neat calculation, and in order not to confuse the reader by diverging too much from Ptolemy. Modern astronomy owes much to Mysterium Cosmographicum, despite flaws in its main thesis, since it represents the first step in cleansing the Copernican system of the remnants of the Ptolemaic theory still clinging to it. Kepler's laws of planetary motion were not immediately accepted. Several major figures such as Galileo and René Descartes completely ignored Kepler's astronomy and nova. Many astronomers, including Kepler's teacher Michael Maestlin, objected to Kepler's introduction of physics into his astronomy. Some adopted compromise positions. His mind-beliedless accepted elliptical orbits but replaced Kepler's area law with uniform motion in respect to the empty focus of the ellipse, while Setward used an elliptical orbit with motions defined by an equant. Several astronomers tested Kepler's theory and its various modifications against astronomical observations. Two transits of Venus and Mercury across the face of the Sun provide a sensitive test of the theory under circumstances when these planets could not normally be observed. Kepler had been extremely uncertain of the parameters for Mercury and advised observers to look for the transit the day before and after the predicted date. Pierre Gassendi observed the transit of the day predicted, a confirmation of Kepler's prediction. This was the first observation of a transit of Mercury. However, his attempt to observe the transit of Venus just 1 month later was unsuccessful due to inaccuracies in the Rudolphine tables. Epitome of Copernican astronomy was read by astronomers throughout Europe, and following Kepler's death, it was the main vehicle for spreading Kepler's idea. In the period 1630 to 1650, this book was the most widely used astronomy textbook, winning many converts to ellipse-based astronomy. However, few adopted his ideas on the physical basis for celestial motions. In the late 17th century, a number of physical astronomy theories drawing from Kepler's work, notably those of Giovanni Alfonso Bernoulli and Robert Hooke, began to incorporate attractive forces and the Cartesian concept of inertia. This culminated in Isaac Newton's Principia Mathematica, in which Newton derived Kepler's laws of planetary motion from a force-based theory of universal gravitation. Coming to Kepler's laws of planetary motion. In astronomy, Kepler's laws of planetary motion are three scientific laws describing the motion of planets around the Sun, published by Johannes Kepler between 1609 and 1619. These improved the heliocentric theory of Nicolaus Copernicus, replacing its circular orbits and epicycles with elliptical trajectories and explaining how planetary velocities vary. The laws come as the first law. The orbits are ellipses with focal points F1 and F2 for the first planet and F1 and F3 for the second planet. The Sun is placed in one focal point. So we can say all planets move around the Sun elliptical orbits, having the Sun as one of the foci. Initially, it was assumed that the planets revolve on the Sun in circular orbits with Sun at the center. But Kepler was the first to suggest that the path of the planets is elliptical. The second law states that the two shaded sectors A1 and A2 have the same surface area, and the time for planet 1 to cover segment A1 is equal to the time to cover segment A2. A radius vector joining any planet to the Sun sweeps out equal areas in equal length and time. We can also say that the areal velocity of the planet is constant. The elliptical orbits of planets were indicated by calculations of the orbit of Mars. From this, Kepler inferred that other bodies in the solar system, including those farther away from the Sun, also have elliptical orbits. The second law helps to establish that when a planet is closer to the Sun, it travels faster. The ratio of the square of an object's orbital period with the cube of the semi-major of its orbit is the same for all objects orbiting the same primary. The third law expresses that farther a planet is from the Sun, the longer is its orbit. Isaac Newton showed in 1687 that relationships like Kepler would apply in the solar system to a good approximation as a consequence of his own laws of motion and laws of universal gravitation. Proceeding further, I would like to give you a brief comparison of his theory to Copernicus. Kepler's laws improve the model of Copernicus. If the eccentricities of the planetary orbits are taken as zero, then Kepler basically agreed with Copernicus. The planetary orbit is a circle, the Sun is at the center of the orbit, the speed of the planet in the orbit is constant. The eccentricities of the orbits of those planets known to Copernicus and Kepler are small, so the foregoing rules give fair approximations of planetary motion. But Kepler's laws fit the observations better than does the model proposed by Copernicus. Kepler's corrections are not at all obvious. The planetary orbit is not a circle but an ellipse. The Sun is not at the center but at a focal point of the elliptical orbit. Neither the linear speed nor the angular speed of the planet in the orbit is constant, but the area speed is constant. Now, a big question arises that how did Newton guess the inverse square rule? Isaac Newton computed in his philosophy Naturalis and Principia Mathematica the acceleration of a planet moving around according to Kepler's first and second law. The direction of the acceleration is towards the Sun. The magnitude of the acceleration is inversely proportional to the square of the planet's distance from the Sun. This implies that the Sun may be the physical cause of the acceleration of planets. However, Newton states in his Principia that he considers forces from a mathematical point of view, not a physical, thereby taking an instrumentalist view. Moreover, he does not assign a cause to gravity. Newton defined the force acting on a planet to be the product of its mass and acceleration. Every planet is attracted towards the Sun. The force acting on a planet is directly proportional to the mass of the planet and is inversely proportional to the square of its distance from the Sun. The Sun plays an unsymmetrical part, which is unjustified. So he assumed in Newton's laws of universal gravitation, all bodies in the solar system attract one another. The force between two bodies is in direct proportional to the product of their masses and is inversely proportional to the square of the distance between them. As the planets have small masses compared to that of the Sun, the orbits conform approximately to Kepler's law. Newton's model improves upon Kepler's model and fits actual observations more accurately. How did Newton guess the inverse square rule? Let us, for this graph actually shows how the dependence can be depicted graphically for gravitational force and the square of the distance. So in order to understand this, let us first of all consider a planet of an orbit of radius r, in the center of which there is Sun and there is the planet. So we find it is important to note that Kepler could not give a theory to explain the motion of planets. It was Newton who showed that the cause of the planetary motion is the gravitational force that the Sun exerts on them. Newton used the third law of Kepler to calculate the gravitational force of attraction. The gravitational force of the Earth is weakened by distance. A simple argument goes like this. We can assume that the planetary orbits are circular. Suppose the orbital velocity is v and the radius of the orbit is r. Then the force acting on an orbiting planet will be obviously given by F equal to mv square by r, that is the centripetal force, as m is constant, so we can write F is proportional to v square by r. Mark it as equation 1. Now if t denotes the period of revolution of the planet, then t will be equal to 2 pi r by v, or v is equal to 2 pi r by t, isn't it? Where 2 pi r is the distance travelled in one round. Now From the first equation, as we have got that f is proportional to v square by r, let us square this term. So we will get v square equal to 4 pi square. 2 pi is 4 pi square. That will be 4 pi square r square by t square. As 4 pi square is constant, therefore v square is proportional to r square by t square. So we can write down v square is proportional to 1 by r into r cube by t square. Now from Kepler's third law, r cube by t square is constant. Therefore, v square is proportional to r by r. Mark it as equation 2. Now just compare equation 1 and equation 2. In place of v square, we can write down 1 by r. So finally, we just clear it up. So we can write down f proportional to v square by r. So now we can write down f is proportional to, in place of v square, we can write down 1 by r. Now obviously there is 1 by r more, so we get f is proportional to 1 by r square. So this is inverse square law. So this is the manner in which the dependence between the force of attraction between two objects and the distance of separation between the two masses. This was obtained by Sir Isaac Newton, by Newton using Kepler's third law. So let's stop our discussion for today at this point. Thank you.